This example is on forecasting a time series with trend using linear regression. So the example is using 12 time periods, 12 months, January through December. And here are the actual forecasts of certain product or sales in thousands maybe. But because when we're doing forecasting, the time series requires numbers, we don't use January, February, March. We use numbers, so we have to put 1, 2, 3, 4, and so on, up to 12. So the idea when a time series has trend and is not just random component, we cannot use moving average or weighted moving average or exponential smoothing. Even though those techniques you can adjust for trend and seasonality and other components, in this class we use them only for random components. We use linear regression when the time series has trend. For example, in this time series, if we plot it, and this plot is by hand, so it's not as good as plotting it in Excel, for example, we notice that the sales or the actual demand is going up. So visually, we do notice that it's going up. It's not flat. So that's a good thing, but we cannot really confirm that it's going up unless we do it statistically. So the idea is we can use linear regression to fit a straight line. This is where the word linear comes from the word line, to this time series. So if we look at this time series and try to predict the best fitting line here to this time series, and I'm just going to draw it, a line can be represented, a straight line can be represented as y equals a plus b times x. X is time, so that's 1 through 12, and that's the period 12 here is the last period we have on the time series. And y is the sales, which is in this case the actual demand, A. The idea is if we have a straight line, then we can extend it, and then we can find period 13, which is January of next year, 14, which is February of next year, and so on. So we need to find the A and the B. A is the A-intercept is the Y-intercept, and B is the slope of the line. So that's the two things we need to find. A is where the line intersects the y-axis, and B is how much is the line slanting from the x-axis. So the first thing to do is to calculate A and B of this trend line. And those are calculated using least square error. That's why it's called the least square error regression line. So the least errors from the time series to the line will give us the best fitting line. And so there are two ways to do this. The way that is described in your book, using formulas that you learned in statistics, and they will require you to do a lot of calculations to get A and B, or you can use Excel to do that. And there are again multiple ways to do this in Excel even. In Excel you can use a trend line, just clicking on the points and getting trend line. You can use the Linest formula. You can use the data analysis pack, which is an add-in. and using regression. Again, all these I assume that you took in the econ class, the statistics class, so we don't go into details in these, and they're really not required to cover in operations in DS350. So I'm going to assume that for this you learned about it in statistics on how to calculate, and for this you learned about, again, in statistics or the econ class, how to do it in Excel. The good news is we're not going to rehash this in this class and relearn how to do it. We're just going to be using the A and B. And so even though the solutions in your book for the examples and for the practice problems, the solutions that are posted on Blackboard are using the formulas, I'm going to assume that you can understand how to read this. So I assume that you know how to read the regression output from Excel. And so, and you can find what little a and little b are. And I may do another example and write the important parts of regression output just to check. So for this problem, when we run data analysis and regression on this, we get that little a is equal to 35.21 and little b is equal to 1.72. And as you can see, even with my graphing, which is not very accurate, it almost hits it at 35, and the slope is 1.72. So my equation for the line then is y equals 35.2 1, but let's just go with 1 decimal, plus 1.7x. That's the equation of the trend line. So if I do want to find what is the forecast for period 13, for example here, all I have to do is y for period 13 is 35.2 plus 1.7 multiplied by 13. So that would give you 57.6 almost. Okay, that would be January of your next year, the forecast for January of your next year. Can I do February of next year? Absolutely, you can. 35.2 plus 1.7 times 14. March, same thing, 35.2 plus 1.7 times 15. And so on. You can go as far as December. So that would be 24. You can go as far away in the future as you want to be able to calculate the forecast. But the more in the future you go to calculate the forecast, the less accurate you get. But at least you are able to do that because you can extend the line and calculate the forecast. So whereas you were not able to do that with moving average and weighted moving average. So this is the technique that is used, for example, to forecast budgets for the next year, for 12 months of the next year. Now the rest of it is exactly the same like previous example. So I can come here and start calculating forecasts from as early as period 1. So I can come here and again put A is 35.2 and B is 1.7, and either I'm doing this in Excel or by hand. So for this forecast it will be 35.2 plus 1.7 times 1. The answer would be 36.9. That's a forecast for period 1. 35 35.2 plus 1.7 times 2, that would be 38.65, and so on. And so I can calculate the forecast for every period, then calculate the errors, calculate the bias, MAD, MSE, sigma, do the entire error analysis just like any other techniques, draw control charts, everything else becomes the same, just like moving average or weighted moving average or exponential smoothing.